Hello, everyone. My name is Schatz, and I'm going to be talking a little bit today about modules. So modules are an algebraic structure that are very much a natural evolution of groups and rings. And the basic idea is sometimes in math, we want to have binary operations that are happening between two mathematically dissimilar objects. For example, when we multiply a number by a matrix, it would not really be sensible to try to understand that operation as a ring operation. So we kind of need to come up with some generalization. And by mentioning a matrix, I've already suggested a connection to linear algebra. And we can, in fact, understand a vector space from linear algebra as a certain type of module. And so we're performing this exercise of redefining linear algebra in the terms of abstract algebra in the hopes that we might gain some new knowledge. And in particular, we are going to derive an alternative proof of the rank nullity theorem that I personally find quite satisfying. So let's get into it. So to construct a module, we start with a ring and an abelian group denoted additively, and we give them a second binary operation called scalar multiplication. Now, typically we understand a binary operation on a set S as a function from S cross S into S. But here, this binary operation isn't quite the same thing. We have a function from the ring to the abelian group, which function from the ring cross the abelian group to the abelian group. And we require that the addition and multiplication be compatible in a specific sense, in much the same way that we require ring addition and multiplication to be compatible with each other. So superficially, this looks a lot like a ring, but it is this subtle difference that makes the two structures, modules and rings, very different. So a few notes: those subscripted binary operations are quite cumbersome to use regularly, but they were great for the clarity there in the definition and for future definitions. We also could have defined a right-sided R module where the scalars are on the right side of the module elements when you multiply them, and we would have gotten essentially the same structure. So you'll notice that I will constantly refer to these as modules. The proper term is R modules, but that's again a little cumbersome. The reason we like this so much as mathematicians is because, well, even though A is the module, its structure as a module is very much dependent on the ring in question. We should also note that the trivial group is a module over any ring R. And the concept of a vector space from linear algebra is completely analogous to a module over a division ring. And typically in linear algebra, you will also assume that we're talking about a field, not just a division ring, because in many applications, well, that simply is the case. Usually you're talking about the real over the complex numbers, which do have commutative multiplication. So we need to proceed through a few more definitions surrounding modules. The first one is very much like something we've seen in group theory. All this slide is saying is that we can endow the cross product of modules with a valid module structure by using component-wise addition and scalar multiplication. And it is not hard to verify that this works out, but a little tedious. This is abstract algebra. We are, of course, going to need a concept of a homomorphism. And the way we can do that is much like how we do homomorphisms for rings. We simply require that the function be operation preserving for both addition and scalar multiplication. Notice that this is telling us that any module homomorphism is a homomorphism of just the abelian groups as well. So we can use anything we know about group homomorphisms and apply it to module homomorphisms. And so a linear transformation from linear algebra simply reduces to a module homomorphism of vector spaces. And an R module isomorphism, of course, is a bijective homomorphism of modules. So this is our most foreign definition. An exact sequence of module homomorphisms is simply 5 modules in a row, all over the same ring R, with homomorphisms going between them. And we say it's exact when if we take any homomorphism in the sequence, if you look at its range, that is the kernel of the next homomorphism in the sequence. When the outer two modules are the trivial module, we say that this is a short exact sequence. And these are what we're really going to be studying here. Now, don't get scared because I've got unlabeled arrows here, but they are in fact unambiguous. Let's think about that. So a homomorphism going between these two sets, well, 0 has to be mapped to 0. And a homomorphism here simply has to map everything in C to 0. And that forces F and G actually to behave in a certain way because of exactness. In particular, if we look at the range of the unlabeled arrow here, that has to be 0, which has to be the kernel of F. So F is injective. And the range of G here has to be the kernel of the unlabeled arrow, which is all of C, because everything in C is getting mapped to 0. So for a short exact sequence, F is injective and G is surjective, which we're going to use all the time. Now, we want to introduce some kind of equivalence relation on exact sequences themselves, not just the modules. And that's obviously going to involve module isomorphisms going between each component of the sequence. But we also want something to kind of make sure that the module homomorphisms themselves are behaving similarly in between both sequences. And the way we're going to do that is with this property called commutativity. So we say the two exact sequences are isomorphic when there exists these alphas, which are isomorphisms, if they exist, and they have to make this digraph commutative. And when we say commutative, we mean that every rectangular subgraph, say this one here, for example, has the property that if you take an element in the top left and you go along either path to the bottom right, you end up at the same element of the bottom right. So formally, we would say alpha 2 composed of F1 is G1 composed of alpha 1. And the same for all the other subgraphs. So this is obviously a lengthy set of conditions to check, and we would like to shorten it. And we can do that with a lemma called the short 5 lemma, which we're going to prove now. So we have as global assumptions that these are all modules with the same ring R with module homomorphisms depicted by the arrows. We also assume that the digraph is commutative everywhere and that each row is a short exact sequence. So the claim is that if the outer two homomorphisms are injective, surjective, or bijective, then the center homomorphism satisfies the same property. Obviously, claim 3 follows from the first two quite trivially. And we're going to look at just the proof of the first claim here in the presentation. The second is very similar. It involves a lot of the same ideas. However, it's a bit longer. So suppose the outer two homomorphisms, alpha and gamma, are injective. We're going to let B be in the kernel of B. So let B be mapped to 0 by beta. And we're going to try to show that B is 0. Standard thing to do when you're working with a homomorphism to show that it's injective. So what can we do here? Well, we have B and B getting mapped to 0 and B prime. We can take its image of 0 under G prime is, of course, 0 and C prime. But we know from commutativity that B going along this path is the same as B going along this path. So we also have gamma composed with G of B is equal to the 0 and C prime. That's helpful because gamma is, by assumption, injective. So we can pull that back and say that G of B is 0. And that is helpful because we can now use the top row being a short exact sequence. So this is saying that B is in the kernel of G. So that means that B is in the range of the previous homomorphism sequence, which is F. So that, of course, means that there is an A in A that is getting mapped to B under F. Now, why is that helpful? Well, A going along this path has to end up at 0 because we've got A going to B, which is going to 0 by hypothesis. So we can also go on the other path and end up at 0. That, of course, is helpful because we know f prime is injective, the bottom row is a short exact sequence, and alpha, by assumption, is injective. So that means A itself has to be 0. A up here has to be 0. So then, of course, the 0 in A must be mapped to 0 in B, and so B is 0. Now, the short five lemma is very useful in proving another lemma called the splitting lemma, which is essentially a generalization of the rank nullity theorem. But we need one definition to facilitate discussion of that lemma. So we say that a short exact sequence is split exact if it is isomorphic to this specific exact sequence. We of course know what the direct sum is here. These homomorphisms here, so I1, I mean the canonical injection from the first factor. So that is taking everything in A1 and mapping it to itself across the 0 of A2. And the projection onto the second factor here, well, that is taking everything in the cross product and mapping it to its second factor. These are in fact modular homomorphisms, and it's pretty easy to see that. So again, this is a lengthy set of conditions to check, and the splitting lemma will give us some alternative conditions that are maybe easier to show. And at the same time, the splitting lemma is also a generalization of the rank nullity theorem. So the splitting lemma. It's in all of the following are equivalent theorem. The first condition being that the given sequence is split exact. The given short exact sequence is split exact. The second condition is there exists an R module homomorphism K, which is a left inverse for F. Now, if you know your set theory, you know that F simply being injective is enough to say that it has a left inverse as a function. But what's important here is one exists that is a homomorphism of the module in question. And we have the same idea for G here, the surjective function having a right inverse, which is a homomorphism, rather than simply a function. So naturally, this is going to be a long proof because it's not all the following are equivalent proof. So we're just going to look at 2 implies 1 in this presentation. So suppose we have a K, which is a homomorphism and a left inverse for F. We want to show that the given sequence is split exact. We need to show that these 2 short exact sequences are isomorphic to each other. In particular, we need to define a phi, we don't have one yet, that will make this digraph turn out to be commutative and have phi being an isomorphism. Now, what would we want phi to be? We obviously have to use homomorphisms we're given, but it's not exactly clear at first what we would choose. Of course, probably the best clue is to look at the fact that phi has to have a domain B. So we're going to have to use the homomorphisms here, which also have domain B. So in particular, we can take K, which is going on to the first factor here, and G, which is going on to the second factor here, and maybe turn that into phi. And in fact, it works out that if you define phi to be K cross G, so to speak, it works out. Now, note that there are actually 2 reasons why we want to establish commutativity at this stage. I said that we need it to establish that these 2 short exact sequences are isomorphic. However, we also want to, because if we can show that this is a commutative digraph, we can actually invoke the short file lemma, right? Because we've got identity functions on either side here, which are bijections. So if this digraph is commutative, then phi is an isomorphism as well. We won't even have to worry about verifying that this is an injective homomorphism. It is, of course, clearly a homomorphism of the modules in question. So let's look at establishing commutativity here. If we look at the left subgraph, we can evaluate phi composed with F. And well, just by the definition of phi, that's going to be K composed of F cross G composed of F. And by assumption, K composed with F is the identity function. So we have that in the first factor. And thinking about exactness here, everything in F, everything in the range of F is ending up getting mapped to 0 by G. So phi composed with F is just the projection, the canonical injection from the first factor, which is in fact what we wanted it to be here, right? So looking at the right side, we have pi2 composed with phi. Well, we just projected onto the second factor. That is in fact G, and that's exactly what we wanted. The other path is just the identity composed with G. So as I said earlier, we just invoke the short phi limit and we arrive at phi being binary. So the given sequence is in fact split exact. Now, I mentioned earlier that this theorem, or this lemma rather, is a generalization of the rank nullity theorem. And that would seem quite surprising, right? Because this simply looks nothing like the rank nullity theorem. But it is in fact correct to say that it is a generalization of the rank nullity theorem. And the key idea here is that the splitting lemma will allow us to prove a deep fact about short exact sequences of vector spaces that will help us prove the rank nullity theorem. So think about a short exact sequence of vector spaces. We're actually going to show that it must be split exact. We're going to use the splitting lemma. In particular, we're going to use the conditional we proved 2 implies 1 to do this proof. Now, this is easily the most technical proof of the paper. So we're just going to look at the basic idea here in the presentation. So suppose we have a short exact sequence of vector spaces. The idea is that every vector space has a basis that is a linearly independent spanning set. And in general, as an aside, a module need not have one. And the fact that vector spaces have a basis is important because it interplays with the abstract algebra we've been developing here. So let beta be a basis for V. And we're going to think about what happens when we take beta's pre-image under T1. Now, every basis vector in beta is either in the range of T1 or not. If it is not in the range of T1, well, then it doesn't have a pre-image. If it is in the range of T1, T1 is injective, right? So that means that the pre-image is unique. You can manipulate that fact to actually show that beta prime itself is a basis for U. And so we're going to do a standard thing in linear algebra, define a linear transformation by specifying its action only on a basis for V in this case. And we're just going to look at if this basis vector in V, in beta, which is in V, if it's not in the range of T1, then we're just going to map it to the 0 vector in U. If it is in the range, we'll map it to its unique pre-image. So now let's think about what happens when we take this basis beta prime for U. If we take it through T1, we end up with the basis beta for V. And if we take it back through K, it's actually going to map everything right back to where it started. So that is telling us that K composed with T1 of beta prime is actually beta prime itself. And that is telling us that we do, in fact, have a left inverse K for T1. Now, this is a complicated proof, but it allows us to produce a very simple and easy to understand proof of the rank nullity theorem that I would love to share with you. So, the rank nullity theorem states that the nullity, the dimension of the kernel, plus the rank, the dimension of the range, is the dimension of the domain space. So, we're not given a short exact sequence, so we're going to have to make one. We're going to let U be the kernel of T, which is in fact a subset of V, of course, and let W prime be the range of T. And we're going to define J to be the inclusion function. So that's like the identity function, but it would be improper to refer to it as such because the codomain here is not U, but a larger set that contains U. Now, I claim that this is a short exact sequence of vector spaces where the hook arrow is the inclusion function. This works because, well, let's think about exactness going across U. That works because J is injective. It's like the identity function. And going across W prime, well, T is surjective by construction, we could be paring down W to just the range. Now, exactness going across V, well, that's not so hard either, because the range of the inclusion function is just the domain U, which we defined to be the kernel of T. So it works out that this is, in fact, a short exact sequence of vector spaces. And by the theorem we just proved, the sequence is split exact, and we have the center module of the exact sequence isomorphic to the outer two, which are the kernel of T and the range of T. And so then the rank nullity theorem follows immediately from that. So at first glance, it seems we've actually proven a stronger claim here. But using purely linear algebraic methods, it would not be hard at all to prove this claim, especially once you've already established the rank nullity theorem. What we have done is built a highway of sorts. So if we think about the traditional proof of the rank nullity theorem from linear algebra, that is a very complicated and subtle argument. And it's easy for students to get lost in the details. So it's kind of like driving on a two-lane country road. You know, you can't go very fast. It didn't take long to build the road, but you can't go very fast. And there's bumps along the way. When we introduce our high-powered abstract algebra tools to tackle this problem, we had to spend considerable time and effort to develop them. You know, we had to spend time wrapping our heads around the concept of a module and then working through all these seemingly unmotivated definitions like the exact sequence module homomorphisms. But once we go through all that work, then we get a highway that is really easy to travel on. In particular, we've really shortened and simplified a lot of proofs here. Think about everything we've done has simply been chasing elements around digraphs or verifying commutativity or something simple, something set theoretic like that. So I hope you enjoyed this alternative perspective on linear algebra. And I'd like to thank you all so much for taking the time to watch this presentation. I would like to especially thank Dr. Scherer for all of her great help in putting together this presentation. I really could not have asked for a better advisor. Thank you so much.